Hey everyone. In this video, I'm going to talk about estimation and uncertainty in surveys. And we talked about surveys quite a bit in previous weeks, particularly in the context of the recent presidential election, where we looked at a bunch of examples of predicting likely election results based on polling data prior to the election, right? And the underlying goal here essentially was to infer public opinion in the population, which in of itself in total is not directly observable, based on a survey that basically just asks a sample of the population, right? So in other words, what we want to do, or more generally, what we want to do with survey sampling, is to estimate the unknown value of a quantity of interest of some measure of public opinion in the population, for example, using the data that we have, using our observed sample, right? Overall, or in general, we refer to the quantity of interest in general. It doesn't have to be, presidential approval or preferences for a particular presidential candidate. In general, we refer to any quantity of interest that we try to estimate, that we try to make inferences about, as a parameter, and the method to compute its estimate as an estimator. Okay. So in this general framework, of course, the obvious question to ask is how good our estimate is for the parameter, for the unobservable parameter that is out there in the population. How good is our estimator, right? And ultimately, this is a very difficult question to answer because we don't know the true value of the parameter. So we can't really use it as a comparison to compare our estimator against. It turns out, and this is basically what we're going to talk about in this video, that there are a couple of ways to characterize how well the estimator will perform over hypothetically repeated sampling. So suppose we were able to repeat our survey 1,000 times or repeat our experiment 1,000 times, and we can characterize how our estimator would behave over these repeated sampling procedures. And that's ultimately what we're going to focus a lot on in this video as well as the following videos. Okay, so ultimately what this section will do is it will show you kind of the basic statistical theory that can help us investigate the performance of an estimator that we used basically in previous weeks, right? When we looked at estimating presidential approval or estimating preferences, voting preferences, and things like that. We just looked at point estimates so far, but now we will look at how good is that inference and how much uncertainty is there around this point estimate that we talked about in the past. Okay. And ultimately, and I kind of already alluded to that, this ultimately, this is kind of the core of what we mean by statistical inference, right? Statistical inference, it means that we're guessing what we do not observe from what we do observe, right? So another word of putting that is we're using the data that we have, which is the sample that we can actually collect with 1,000 respondents or 2,000 respondents, to learn something about the data that we don't have, about the total population. For example, in the context of the U.S. elections, the voting age population in the United States. Okay. In this kind of quest of guessing what we do not observe from what we do observe, what we want to estimate is in general usually referred to as a parameter. In our case, in the general case, we often denote this as theta. This is unobservable. This is the parameter that exists basically in the population, but we can't observe the entire population. What we do observe is just some data, which is usually, in the context of surveys, just a random sample of observations, okay? And we use these data, we use this sample to compute an estimate of this parameter. And we usually denote this estimate of our parameter as theta hat. So any of our estimates gets a little hat to make clear that this is not the true parameter in the population. This is our estimate, our best guess of that parameter that we're trying to make inferences about, okay? And now again, the key question for us here is how good is theta hat as an estimate of theta, right? And as I mentioned, ideally, if we want to know how good an estimator is, ideally, in an ideal world, we could just look at the estimation error, right? We could just compare our estimate to the true population parameter theta, or here as theta naught, where basically theta naught is the true, or theta 0 is the true value of theta, okay? So in an ideal world, we would just compare our estimator to the true value of theta, and that would tell us how good our estimator is. Of course, the problem is that theta is unknown. We don't know the true population parameter. So how can we ultimately say whether our estimator is good or bad, okay? The good thing is we're not stuck here, right? We can't, we can still kind of make assessments of our estimator, or our, the quality of our estimator, even though we don't know the true population parameter theta, or theta 0. Okay, so how are we going to go about this? What we're going to do is we will look at two hypothetical scenarios, kind of extrapolating beyond our individual sample. The first question we're going to look at is how well would theta hat perform as the sample size goes to infinity? Right? What happens if we, hypothetically, were able to collect a larger and larger sample, so to speak? And the second question, or the second hypothetical scenario that we're going to look at, is how well would theta hat perform over repeated data generating processes, right? And ultimately, a lot of kind of our inferences, or when we talk about quantifying the uncertainty around our estimate, what we're talking about is the uncertainty kind of in the sampling distribution, which is the distribution over these hypothetically repeated data generating processes. And we'll go through a couple of examples to kind of get a better idea of what exactly that means. So let's go back to one of our examples that we talked about in previous videos, as well as in our readings. Specifically, we're going to talk about the polling disaster of the 2016 election, where all major pre-election polls predicted Clinton's victory, but of course, Trump won the election in 2016, right? And we talked also in our Q&A session, we talked a bunch about different reasons of why that was the case, and what ultimately happened. And we also talked, of course, about the 2020 election. And in our Q&A session, we can maybe kind of transfer and talk a little bit more about the most recent election. But we'll focus on 2016 for now. So what happened in 2016 that kind of led to this big discrepancy between the pre-election polling result, which kind of predicted a victory for Clinton, and the actual result of what happened in the election? There are a couple of factors that we can bring in. We have James Comey's announcement about the Clinton email scandal right before the election, which of course had a huge impact on parts of the electorate. We have an issue of non-response bias in the pre-election polls, where certain people were unwilling to participate in the polls, and those people were more likely to support Trump. We have social desirability bias, but there's still some debate kind of in the literature on how much social desirability bias there was back then, and certainly how much there was now in the 2020 election. But at least to some extent, people might not have been kind of willing to admit in surveys that they wanted to vote for Trump, even though they later on did. And the last part that we can that also played a role was the failure to predict turnout, right? So in a lot of these polls, there's this distinction between support among likely voters versus support among registered voters, and there were quite some discrepancies in predicting who were going to turn out, and ultimately, of course, that led to biases in predicted support at the polls. Okay, so those are all reasons why the polls were off. But now what we want to do is ultimately we're going to look at one specific example, particularly the ABC News Washington Post poll that was done just a few days before the election, It was conducted November 3rd to November 6th, and the election in 2016 was on November 8th, right? And now we want to look at how large this deviation was between our polling result and the actual result in the election, right? And to what extent the deviation was kind of within the realm of deviations that you would see by chance, or to what extent we would argue, okay, there's something else something more systematic that ultimately went wrong, right? So we're just going to do this on the basis of one particular example, the ABC News and Washington Post poll. It had 2,220 likely voters. It was a live phone interview, and the results in that poll, at least, were that Clinton, and this is now, we're going to look at overall popular vote results, right? So we're looking at overall result across the entire nation, popular vote results. And we're not looking at, you know, individual statewide predictions the way we did it in previous weeks. So we're look at it in a more, you know, general sense. Okay. The prediction based on that poll was Clinton in the lead, 47%, Trump 43%, Johnson, third party candidate, at 4%. And the margin of error reported in that poll was plus or minus 2.5 percentage points. And we're going to get back to what exactly this margin of error exactly means in a second. It turns out the actual election results, again, focusing now on the popular vote, not electoral college, was that Clinton received 48% of the vote and Trump received 47% of the vote. So in terms of support for Clinton, the deviation is not that large because of, you know, the third, but because of the, you know, third candidate and basically the lack of support for Johnson, we see a much higher percentage in the popular vote for Trump, 47% as compared to 43% that was predicted in the ABC News Washington Post poll, right? So what we're going to look at here now is to what extent this 43% support for Trump was kind of within the realm, this deviation within the realm of what you could, you know, theoretically observe just by chance, or to what extent there was likely to be some systematic deviation between the actual election result and this polling support presented in the polls. Okay. Okay. Let's see. Maybe I'll. Okay. Let's maybe I'll take a quick break here, then you have a 10-minute video now, and I'm gonna jump right back into estimating Trump support and going through that in a new video. So I'll pause here and I'll continue in the next video.